All right, welcome back, everyone. So today we are actually going to cover our very first machine learning algorithm, and that is going to be for linear regression. This big blank area out here is going to be kind of like a blackboard that I'm going to be kind of putting down all of the notes and everything by hand, just like I would on a whiteboard. So the purpose of this is for that, and then as if we get far enough, we're actually going to do the Python code for linear regression, and I'll replace the blackboard with Spider, so you can actually watch the code in action. So, alrighty, here we go. Let's get started. So first off, what do I mean when I'm talking about linear regression? Well, linear regression, I briefly mentioned it when we were doing the overview of machine learning. This is one of the two main methods that I talked about that was listed under the supervised learning. So this is supervised learning, which means we are going to supervised. I'm a terrible speller. You'll learn that as we go. Supervised learning. And supervised learning means that we have labeled data. And for the example that we're going to be looking at, we're going to be looking at house prices. So we're going to have some data points, and this is going to correspond to, on the x-axis, the square footage of a house, and maybe this is 1,000 square feet, 2,000, 3,000, 4,000. And then over here, we're going to have the price of the house. And maybe this price, I'll do it in thousands. So this is 100, 200, 300, and 400,000. So thousands. Alrighty? And so what we have are some data for houses that have actually sold. They had a certain square footage and they sold for a specific price. In this case right here, the house looks like maybe it had about 2,600, 2,700 square feet, and it sold for about 250,000, 260. So these are actual labeled data points, and linear regression's whole purpose is to fit a line to the data. You want to fit the best line possible. So a good fit for this data might be some line maybe that does like that. That's not the best fit I could have done, but we'll work with it. So with this data right here, if I have a line that fits the data the best, I can now say, well, what if I have square footage that is exactly 3,213 square feet? What kind of price should I be able to get for that? Well, with a line, this line right here, I should be able to plug an amount in and get a price out, an amount of square footage in and get a price out. So if I have a line that best fits the data, I can then make a prediction on what price I would get. So that's the name of the game for what we're going to be doing with linear regression, the initial example that we're looking at anyway. So this is going to be a very simple example. We're going to make a lot of assumptions, so bear with it, but I think it'll work out fairly well. Alrighty, so let me go to the next slide. Alrighty. So before we can really jump into linear regression, we need to have some terminology that we can use. This is terminology that is used in all of machine learning. You will hear it for everything that we'll be doing in machine learning. You'll hear this. So it will be things like training set. So a training set is just a set of all the data that we're using to train our model. Each one of the data points inside of the set of data is called a training example. So we will be referring to training examples a lot as we go. I can't tell you how often we're going to be referring to that. So training example is definitely something that we want to get used to. And all it means is a data point. So in the case of the example we have above, each one of these little X's was a training example. Alrighty? So we keep going, and then we get to M is the number of training examples in your data set. This is unlike any other class, any other mathematics, computer science that I've ever seen. Every one of those uses N as the number of training examples. Right? Everyone is used to N equaling the number of points or whatever. But in machine learning, we don't use N, we use M. I really don't have an answer why. It's just when you read papers and books and everything on machine learning, you'll see that M is what they use to designate the number of training examples. It just is. So we're stuck with it. So other than that, we have something that we're very familiar with, in that we have X as our input variable and Y as our output. That's typical for just about all of mathematics. You're going to have your independent variable be your X, and then the dependent variable, which depends on what value you put in for your X, is going to be your Y. But in machine learning, sometimes we don't just say X and Y as input and output. Sometimes we say that X are the features and Y are the targets. So X equal features and Y is the target. Okay? You'll get used to it after we go through this enough. Now, for the next weird thing about machine learning, I am going to mess this up consistently. It's just going to happen. Just please cut me some slack with this, because this is there's nothing I can do about it. Machine learning does not use subscripts to represent the variable that you're looking at. So in all of mathematics, we use x sub 1, x sub 2, x sub 3 to indicate which x we're talking about. Machine learning uses superscripts. So in machine learning, it makes perfect sense to say x1, superscript 1. This means this is the first x, the first input, or the first feature. All right? So same goes with y. You still have to do the same thing. This would be the second y. I know, this bothers me too. At least I hope it's bothering some of y'all. This drives me insane. The reason behind this, it actually makes sense. When you get to very complicated models and we're using linear algebra to represent things, this superscript notation is going to lend itself very, very well to that. Like when we get to neural networks, for example, the superscript makes a lot of sense. However, I have been the product of mathematics for decades now, and I can tell you I'm not going to say x superscript 1, y superscript 2. I'm going to say x sub 1, y sub 2, maybe x1, y2. There's no way I'm going to say superscript. It just is not going to happen. I'm not used to it. I've been doing machine learning for years now, and I still can't get used to it. So it is just going to be a plain old, I'm going to say x sub 1, y sub 2, or x1, y2, just the way it's going to be. And so when we combine the x and y in an ordered pair, we actually have a training example, because each of these training examples consists of an x and a y that are given, labeled, in other words. So that's where we stand with our terminology. Then we're going to learn several other terms today that are going to stick with us for the rest of the course. So give it this an extra look over to where it sticks. I'm going to be using the words training example, M, representing the data, the individual data points with the superscripts consistently from here on. So get used to it. You're going to see it quite a bit. So with that, let's go move a little bit further into things. And so we're going to start off talking about what's called a hypothesis function. And if you'll allow me, I'm just going to erase this terminology set of scribblings here on the board and leave the example up top. So let me just erase this. Erase. All right. So when we're talking about a hypothesis function, the hypothesis function, all it does is it maps x's to y's, inputs to outputs. Okay? So we're going to be fitting a line to our data, and so we're going to use for our hypothesis function for linear regression just the equation of a line. That's all we're going to do. So that's nice and compact. We're going to be doing y equals mx plus b. We'll feed in an x, then we'll use the slope, which is what m is. That's the slope. And then the y-intercept, b, where the function crosses the y-axis. If it extended all the way to the y-axis, our model probably won't, because I doubt we're going to have a house with 0 square footage or even 1 square footage. But we'll see that actually sort of makes sense, especially as we go further in. So anyways, this is our hypothesis function. For the rest of the course, the hypothesis function, all it does is it maps inputs to outputs. So whatever you put in, you send it through your function, turn the crank, and out pops an output. In our case, if we feed it some value, some input, some feature that is square footage, we expect it to output the price. And that's what we get when we feed an x into this line, the equation of the line. We feed an x in, we multiply it by the slope, whatever that is, add the y-intercept, whatever that is, and then we have a house price pop out right here with y. Now, in machine learning, we're not going to be using m and b to represent these features. I shouldn't say features because machine learning uses that word, to represent these entities. Instead, what we're going to say is y equals theta sub 0 plus theta sub 1x. Now, these thetas are my thetas. That's one of their subs. When we actually start getting into the machine learning training examples, there'll be superscripts ones. Don't worry. Forget I said it. So theta 0 plus theta 1x, where the y-intercept is theta 0 and the slope is theta 1. So we're going to have that kind of equation set up for our line, and this is now, I can say this equation right here is going to be our hypothesis function that we use for linear regression. Okay? Alrighty. So, what does a hypothesis function do? It maps inputs to outputs. That's all it does. Okay. That is one of the, I guess, 3 or 4 terms that we are going to learn during this process that is going to come up over and over and over again. We are never going to get away from the hypothesis function. Now that we have said what it does, it maps inputs to outputs, we're going to use this term forever for every single model that we do inside the class, pretty much. So that's a hypothesis function and what it does, its function. And so with that in mind, we can go to the next slide and see what's up. All right. cost function. You're going to like this. So I'm now going to erase pretty much, I think I can get by with the bottom part and leave the top part. So let's say, actually I'm going to erase some of this. I'll leave some, but I'm going to erase all the data points. Alrighty, so let me go ahead and draw some data points. I'm going to draw, if I actually have my pen, I'll just draw 3 data points, and I'm going to fit a line through those data points, okay? Now, how can I tell if this line is a better fit to the data? Then maybe I'll draw it in a separate color so that we're not confusing it. Then that line, how can I tell which one's a better fit to the data? And if you've had any statistics, you already know the answer to this. You can probably just guess it too if you look at it for a second. The way that we quantify whether or not a line is a decent fit to the data is by seeing how much error there is with the line. So when you think about it, if I take, I'm going to just do the yellow for now. If I take the distance between my data points and this guess, this linear guess that I have for the best fit, if I take these distances and add them all up, I can get an idea of how well the line is fitting the data. Once I add them all up, if I have a really high value, it's going to be a poor guess. If it's a low value, maybe it's a better guess. So what I need to do is figure out a way to represent these distances. Now, I can't just do something like x sub I minus, let's see, how do I want to label this? Do I want to do x sub I first, or do I? I'm looking at my notes, because if I don't, x sub I, my goodness, if I had good sense, that'd be dangerous. Hold on, let me erase that. I just looked at my notes and I was like, oh, wait a second. That made no sense whatsoever. Let me try that again. Y sub I know superscript, minus the predicted value from the line. So this is the actual data point. This is the ith output. So it is the price of an actual data point. The hat here represents a predicted value. So this is what I'm going to use to represent the y value that would be predicted from the line itself. Okay? So if I take this and subtract it off, and maybe then I add the other two, like so, just add all these together, then I'm good to go, right? To tell if a line's doing a good job or not? No, that is a terrible idea to add these three together and say that's my error that I'm getting. Why is that a bad idea? Well, it's a bad idea because if the data value happens to be above the line, I get a positive value, but if the data value is below the line, I get a negative value. And then when I add all these together, I'm going to wind up canceling some of the error because some of them are going to be positive, some of them are going to be negative. So I need a better way of doing this. Now, I know some of y'all are screaming, absolute value, use absolute value. Yes, we can totally use absolute value. That would totally work. But there's a big problem using absolute value. The big problem is that the math that we're going to use for the algorithm will not work easily with absolute value. If anyone has ever worked with absolute values in mathematics before, you know what a terrible construction they are to actually work with. They are very difficult to get a handle on. So let's not use absolute value. What's another way that we might be able to do this? How can we represent this distance? Well, what if we simply squared all the differences. If we did that, we would actually have this would be some amount, this would be some amount, and this would be some amount, and all the amounts would be positive. So that would work very well. So I'm just going to add all this up. Well, I can't just add up all of these squared errors. What I want to do instead is to, well, if I have 3 data points and add up all that error versus a model that has 2 data points, the model with 2 data points is going to have less overall error, so you would think that would be a better fit. So I need some way to get this to be able to be compared versus other models. And of course, the way that we're going to do that is by taking the number of training examples that we're running through and dividing by that number. So I'm going to do this in a compact way. I'm going to say this is equal to 1 over m times the summation I from 1 to m of y I minus y hat I squared. Alrighty? Now what this will do is it'll start at I of 1. So then it'll do the first difference, the first error. It'll square it, and then it will add it to the second training example's error. Then it will add that to the third training example's error, and then it will divide by the number of training examples. And that will give me an average squared error, right? Except we don't ever say average squared error, we say mean squared error, MSE. So this is going to be our metric for telling us how well a line fits the data. We're going to be looking at the MSE. And the unusual thing about machine learning is that you don't call error in machine learning. What you do is you call error, I wish I could like make a giant fluorescent sign right here. I put it in a different color. The cost. Underline, underline, underline. The cost is the error associated with a specific guess. So in our case, the cost is going to be analogous to the MSE. And typically in machine learning, you don't just say the cost, you say you have a cost function. Okay? And that cost function is almost always denoted as J. Okay? So J is the cost function that evaluates how well a guess is doing. So in our case, the cost function is the mean squared error. Okay? That's all it is, mean squared error. So I can rewrite this now. Let me erase some of this. Slightly bigger eraser right here. Yeah, I can leave that. So the cost function for linear regression is going to be the MSE, which is going to be 1 over m summation I from 1 to m of y I minus y hat I squared, and that is what we are going to call J. That's our function. Okay? Now, the cost function is how you estimate how well your model guessed when it made a guess. In our case, we're going to just be guessing at, when I say guessing, I'll come back to that. In our case, we're going to be making guesses on different lines through the data. and we're going to evaluate the cost associated with that guess. Okay, a high cost means it's a poor guess. A low cost means it's a good guess. Okay, so that's where we go when we say cost function. Again, add this to your permanent vocabulary. J is the cost function, and the function of the cost function is to evaluate how well a guess performs. Okay, that's what all the cost function is doing. And our cost function is going to look like this now. Okay? Alrighty, so that's, we're getting close now. So, let's see, do I want to go to that yet? Not yet. Let's actually work with this for a little bit. Okay, so we have the cost here. Hold on, I'm going to pause the video so I can clear something and bring something up real quick. So I'm going to pause you briefly as I tread water in the Atlantic Ocean, and I will be right back. Okay, so now we're back. I'm going to make some changes. I have a cat that's trying to get into my lap right now. I have several cats, and they are very affectionate, so every now and then you may see a cat jump into my lap. I'll try not to let it distract me too much. Alrighty, so let's see here. Let's take all of this, clear it, and then kind of start over just a little bit. Because I need some more space to handle all this. So let me clear the whole screen, and then we will jump back in. All right. So first off, let's talk about our hypothesis function real quick. All right, our hypothesis function that we talked about, that was just the equation of a line, and we said that y is equal to theta sub 0 plus theta 1x, where theta sub 0 is the y-intercept, and theta 1 is the slope, right? Okay. Now, I can, instead of saying y here, I can represent that as h of x, right? Because it's a function of the input. So h of x is equal to theta 0 plus theta 1 x, just like that. Okay? Now, if I have my data, and I'm going to simplify my data a little bit. Let's say that for the simplest example, I'm not actually going, this is before we do the actual work. This is just a simple example. But for the simplest example, if I want to develop this, what I'm going to do is have a set of data points. I'll do 3 of them. 1, 2, 3. And these data points are going to be located at 1, 1, 2, 2, and 3, 3. All right. Now, I'm only going to have 3 of them, and I'm going to make fitting a line to this data really simple because I'm going to eliminate theta 0. Where my hypothesis function now is just theta 1x. Okay? So it's just a slope. That's all I need. I have my slope, I multiply it by my input, whatever it is, and that gives me my hypothesis, which is my y value. Okay? Now, this is as simple as I can make it, and you can probably already guess that if we fit a line through this data that passes through the origin, and assuming I could actually draw, which I can't, it's the worst straight line I've ever seen. Assuming this is a straight line, then that passes through the origin, that's going to be the best fit, right? There's no doubt that that is the best fit. And that best fit, what is the slope of that line that is the best fit? Yeah, I know that this best fit, theta 1 is 1, right? A slope of 1. I plug in a 1 for the x. I need to get a 1 out for the y to fit the data point. So m has to be 1. Same for 2, 2, 3, 3. So this theta 1 needs to be 1 for the best guess, all right? Now, let's say that I don't know this. I have no idea what the best guess is, okay? So instead, I am going to, let's find a blue, that's a nice color. Make a guess. Much better, straight line. And I'm going to say that this theta 1 is equal to 0.5, okay? And then I'm going to make a, oops, let's see, where's the, there it is. A different guess, like this. And this one is going to be theta 1 equals 1.5, okay? So I have 3 different lines that are forming. Gosh, I cannot stand that line. Let me try to redraw that. It's going to drive me crazy. There, it's a little bit better. Whew. Alrighty. So I have 3 different lines that I could guess and see what the cost was associated with each of these lines, right? That's actually not that bad to do. So let me go ahead and try that. Let me start with the 0.5. So let's see. J of, well, this is just a function, my cost function is a function of theta 1 now, right? That's all that I have to be guessing with. So J of theta 1 equals 0.5. The slope is 0.5. Well, what is that going to give me? Well, it's going to give me 1 over, let's see, how many training examples are there? 1, 2, 3. I'm going to put 3 right here for a very special reason. And then it's going to be the sum, I, from 1 to 3 of, I'm going to put the guess first and the actual value second for this. So I'm going to do my h of x, my y hat, I, and actually the I would be right there. Let me erase that one out here. Make that a little bit better. H of x, I, there we go. That's my y hat, I, minus y, I, quantity squared, right? Alrighty, but this hypothesis is just theta 1 times x, okay? So all I can now just substitute straight in for that, and if I do that, I'm going to get 1 over 3 to the side, summation I from 1 to 3 of, well, this is just going to be theta 1 xi minus yi quantity squared. Okay? And we can actually figure out what that value is. Now, why did I leave this space in front of this 3? I left the space in front of the 3 for a very good reason. Does it matter if I divide to do my comparisons between different guesses? If I divide by m plus 1, 7 times m, does any of that matter as long as I hold it consistent? It doesn't. It does not matter what I hold constant here, what I put in for the value here in the denominator, as long as it's consistent over all my guesses, some factor of 3. So I'm going to put a 2 right out front here, 2 times m, 2 times 3. There's a very good reason for that 2, which we'll see in about 5 minutes or so. So if you will bear with me, I'm putting the 2 out here. 2 times 3 is a perfect, as long as it is a factor times as long as the m is involved within it. Let me just put it that way. And I hold it for every one of these guesses. I hold it the exact same value. We can still make the comparisons. It changes absolutely nothing. Okay, so what is this value? Well, this is actually not too bad. This is going to be 1 over 2 times 3 times, here we go, h of x of I is just theta 1 x of I. Well, theta 1 is 0.5, right? So this is going to be 0.5 times 1, so 0.5 times 1, if I can write that in there like that, minus 1 quantity squared. That's for the very first data point, this point, that it's looking for the difference right here. This is the error that it's quantifying. The slope times the x value minus the y value, the actual data point's y value. Okay? Now, plus, I'm going to have, now for the next data point, what is my slope? It's still 0.5, so 0.5 times, but now what is the x value? Right, it's 2 minus the y value, 2, and square that, plus, last one, slope 0.5 times, what's the x value now? 3, minus the y value, 3, quantity squared. And now let me put a big bracket here, and a big bracket here. Turns out when I do this math, when I get it all worked out, that this is just 0.58. Okay? That is the total amount of error using the mean squared error formula that I get from this guess with these 3 data points right here. Alrighty? I'm going to erase some of this and then start in with my green line, which, as you can imagine, is way better. Alrighty? So let me go ahead and go to green. If I can find it. There it is. So this is j of theta 1 equals 1. That's going to equal 1 over 2 times, not point, 2 times 3, summation of all this, which I'll just go ahead and do the summation. I don't need to do that. Right here, you already know that. So here we go. Let's do the 3 different points evaluated, okay? So I'm going to go a little bit faster now because the h of x is just theta 1x. So the first one is going to be 1 times 1, which is going to be 1, minus 1, that's the y value, squared, plus 1 times 2, 2, minus 2, squared, plus 1 times 3, 3, minus the y value, 3, quantity squared. And as you can see, I get 0 for the cost associated with that one. Alrighty? Now, let me go to my last one right here. J of theta 1 equals 1.5. Well, that's going to be 1 over 2 times 3 times bracket. Here we go. Now my slope is going, my theta 1 is 1.5, so it's going to be 1.5 times 1. So it's going to be 1.5 minus the y value 1 squared, plus, now it's going to be 1.5 times 2, which is going to be 3 minus 2, that's the y value, squared, plus 1.5 times 3, 4.5, minus 3 quantity squared. And when I do all of that, I get, what do you know, 0.58. turns out it's symmetrical whether or not I'm 0.5 down or 0.5 above from the ideal slope. Okay? Now, why did I do all this? Well, I did all this to show you what the different costs were that were associated with different guesses. But there's more to it than that. So let me go to a completely different area. I'm going to, if y'all are okay with this, kind of lock this picture in your head, what we have here. And I'm going, actually, you know what? I'll keep it right there. I just need to translate these values here into a very strange looking graph. So let me erase this right here, okay? Erase, erase, erase. All right, we'll make a graph now. So my graph is going to be something that looks very strange. Okay? On the x-axis, I'm going to have theta 1 values, okay? You know what? Let me change one thing about this graph before I get going. Let me come over to like so. Yeah, make it shifted a little bit. Okay. So these are going to be theta 1 values on the x-axis, and the y-axis is going to be the costs associated with those theta 1. Okay? So here we go. For, let's see, theta 1 is 0.5. We'll say that 0.5 is right here. 0.5. I had a value that was, let me put different values up here. Value of 1, 2, 3, 4. Here we go. So I had 0.58, right? So maybe somewhere around here. All right. Now I had, for my theta 1 is 1, right about here. Theta 1 is just 1, plain old 1. I had a cost associated with that of 0. And then for my 1.5 slope, 1.5, I had again 0.58. Okay? Now, let's see, do I have that written down? Oh, I don't want to have to do that. Do I have to do it? I don't remember having it. I don't have it calculated yet. Y'all don't call me on this next one. I don't want to take the time to go through the actual math, but let me do an orange one. Turns out that J of theta 1 equals 0 matches theta 1 equals 2 because of the symmetry, and that is somewhere around, I want to say 2 or 3. I don't remember the exact value, so I'm just going to put a value for 0 and for maybe 2 right here. Somewhere around here, 2.3 maybe. Okay. Now, if I go out to somewhere in the negative and 2.5, it's going to be more symmetry. You see what I'd get if I connected all of these dots? Absolutely. I would get, if I can do this, something that is a parabola. Okay? So this parabola represents the costs that are associated with specific slopes, specific theta 1s. Okay? Now, there's a very good reason why I did all this work. I'm doing stream marks all over the page. I'm going to use this graph with a very clever algorithm to figure out what the best slope is. Not a guess, but what the actual best slope is. All right? So I'm going to erase all this stuff down here, and we are going to move to that algorithm. Okay. So here we go. Let's see. Where do I want to go? Right there. All right. Yeah, we'll go straight for it. All right. So the very next thing that we want to do is go to the very last slide that we're going to cover today and talk about gradient descent. Okay? Gradient descent. If I actually go to the program, that would help. Gradient descent. Okay? Now, gradient descent is the last of the big major terms that we're going to cover for machine learning today. It is used in almost all algorithms in some form or another. And what gradient descent's purpose is, this is an algorithm based on mathematics. I'll just abbreviate math. That guides the guesses in the correct direction. Okay? What do I mean by all that? Well, when we were doing these values here for the slope, we knew what the best one was, and we knew how far to go away from it, and so we could get an idea of what the best one was and all this. But let's say we didn't know any of that. Let's say that I pick a theta 1 value at completely random. I think the best theta 1 value to start with is 0, or I think the best theta 1 value to start with is negative 213. Doesn't matter. What gradient descent is going to do is it will slowly, gradually adjust the guesses that the program makes in the direction of the best guess. Okay? It uses math. It does not guess randomly. It uses rock solid calculus to do this. Okay? So, what does the algorithm look like? Well, the gradient descent algorithm, which is what we're going to cover, is theta sub j gets, this is almost like programming right here, theta sub j minus alpha times, here we go, the partial derivative of the cost function with respect to theta sub j. Okay? Now, the partial derivative, I should say. I don't know if I said the word derivative or not. We just like went from something very simple, we just jumped off a cliff and went straight into calculus. But it's not as bad as it looks. So what gradient descent is going to do is it's going to slowly work its way down to where it comes up with the best guess, okay? I know that the best guess is 1. That is the optimal slope to fit these data points. So what we're going to do is we're going to use this algorithm with an initial random guess, and we're going to figure out, we're going to watch how it gradually descends to the best slope, okay? So I'm going to write that algorithm right up here. Theta sub j gets theta sub j minus alpha times the partial of j with respect to theta sub j. Okay? So let me erase all this now so we can do some math. Now, our first iteration that we're going to look at, this is all that we're going to do for this lecture. We'll pick up next lecture for tomorrow and actually do the calculus and the actual coding in Python. But for right now, we're just going to stick with this kind of very high-level overview of what the algorithm is doing. So this is kind of in pseudocode. This is kind of a programming language. What I should say is this is a new guess. This is the old slope guess. And then we have this alpha thing. This alpha is called the learning rate. Learning rate. Its only purpose is to set how fast we want to converge to the actual answer, the best slope. If we make too large of a guess, we're going to be in trouble. If we make too small of a guess, we're going to be in trouble. I will go ahead and tell you that for a lot of the machine learning applications, a learning rate to start with that's good is 0.1. Okay? So 0.1 is a decent learning rate. Now I've got this thing right here. This is a derivative of j with respect to theta sub 1, which is what we're looking at. Alrighty? Now, there was a reason why I took these values and translated them into these values and then did this parabola. The reason that I did that was because now I can do, since this is a derivative of j, and this is a curve of j, the derivative of the curve is just the slope, right? So now when I have this value right here, I can think of this as the slope. So this is the slope of j. Slope of j. Hope that didn't cut that off, but that's all that is. Alrighty? So let's start with an example. I'm going to make an initial guess for theta sub j. I'm going to start with an initial guess of 1. So let's say the first guess is theta 1 is, did I say 1? I meant 0. Losing my brain. The first guess for theta 1, the slope, we're going to say it's 0. All right? Now, that right there is theta 1 equals 0. And so the slope is going to be represented. Do I have a different color? Let's see, do I have any other color? I guess I can do red. Red's okay. All right. So now I'm going to need the slope right here. Okay. So we're going to say that I've drawn this to scale, because if I drew it to scale, these would be spaced out more, and this would be a little bit steeper. So if I start with a theta 1 of 0, here's what I'm going to get. I'm going to get the new theta. Go back to, so the new theta 1 is going to get the old theta 1, which is 0, minus alpha, which we're going to start with at 0.1, times whatever we think that slope is. I'm going to say that if I had drawn that scale, that slope is going to be around a -2. Okay? Something like that. All right? So the new theta is going to get 0 minus 0.1 times -2. That's going to be 0.2. Okay? So our guess that started here is now going to move to a theta 1 of 0.2. So our new guess is going to be right about there. Make that a big star. All right? So that's our new guess. So now our new guess, our new theta 1, is going to get the old theta 1, which is 0.2 now, 0.2 minus 0.1 times, again, if I draw on that scale, maybe that's negative 1.6, something like that. And so 0.2 plus 0.16 is 0.36, something like that. Alrighty? Now I'll run through it again. And I get theta 1 gets the old theta. This is my new one. The old theta is 0.36 minus 0.1, the alpha, times, now I need my, sorry, I forgot to move. This is where I'm at right now. Well, I moved 0.36, which is somewhere around there. Alrighty. Maybe the slope right here is, oh gosh, I don't know. It's less steep than that, so maybe I just drew an absolute blank. Negative 1.4. I'm just going to make a negative 1.4. I don't want to think. Negative 1.4. So I've got 0.36 plus 0.14 is 0.5. Now we're over here. Okay? Now theta 1 is going to get 0.5 minus 0.1. Maybe now this slope, if it were done to scale, is somewhere around negative 1.2. So it's going to be 0.5 plus 0.12, 0.62. So now it's somewhere around here. Okay. Now the next value, theta 1, is going to be 0.62 minus 0.1 times, maybe that's a negative 1 slope. Okay, so now it's 0.62 plus 0.1 is 0.72. So now it's somewhere around here. Okay? And I can keep going. But what's going to happen? Well, this next one, 0.7 minus 0.1 times, the slope is going to be even shallower. Maybe that's negative 0.8, I don't know. And so I'm only going to go up to 0.8. So I'll be right there. And then the next one, I'm going to have a shallower slope. And so it's going to get a smaller value added to my guess, which will be this value. So maybe it goes 0.8 to 0.86 to 0.9 to 0.93 to 0.95 to 0.96 to 0.97 or 965 to 0.972. I mean, you can see what's happening though. Because the slope is getting shallower and shallower, the amount that I'm going to be adding to the previous slope is going to decrease. And what's going to happen is when I am right about at 1, I'm going to be adding incredibly small amounts to my old slope. As a matter of fact, I'm going to get to a point that is going to be so close to 1 that the slope is going to be almost 0, at which point I'm not really changing my theta values much at all. So theta old, when it is approximately the same as theta new, I stop, because at that point I have reached the bottom of the parabola, which, if you remember calculus, what we just did is we just found the optimal value. We basically, in a parabola, used Newton's method to find our way down to the very bottom. And This is the algorithm. You may have already recognized it as Newton's method, but we call it gradient descent in machine learning because the slope in the direction of a better guess, you can kind of think of it as the gradient because it is the derivative of the cost function. So the way to get to a lower cost function, a lower cost, is by going in the direction of the derivative of the cost. The learning rate sets how fast we move down. And if we use our calculus to do it, we will get to the actual best guess for fitting data every time. And here's one of the things that's really, really cool. If I had made my initial guess instead of theta 0, what if theta 1 equals 0? What if I'd made my original guess negative 712? Would it still have reached the bottom? Yeah, it would have reached the bottom, and it wouldn't have taken that many more steps because at negative 712, this is a parabola. So it's going increasingly steep. I don't even know what the slope would be at theta 1 equals negative 712, but it's a huge slope. So no matter where I start, I'm still going to zero in to the bottom quickly. What about if I start over on this side? Same thing, because if I start over here, let's say I made a guess like this. This is, 2.4 maybe? Theta 1 equals 2.4. Well, now when I do my update, theta 1 gets 2.4 minus 0.1 times the slope, which, I don't know, maybe that's positive 2.4, maybe. I've run out of space. But you see what happens, because now the slope is positive, when I subtract it off using my little subtraction here, I wind up going this direction. So it would go from there to there to there to there to there to there. And it's going to take increasingly small steps until finally it gets so close again that the old is approximately the new and we can stop. Alrighty? So this clever algorithm, which, can't take a whole lot of the credit, Newton came up with this one, will zero in on the best fit for our data no matter where we start our initial guess. It can be completely random. Most people start their initial guesses at 0, just because there's no real reason for it. It's as good a guess as any. But no matter where we start our guess, we will gradually zero down until we are right at the best guess. So there you go. That is what it's all about. I hope you enjoyed this. We have worked our way through the basics of linear regression, terminology that we'll be using in machine learning, and 3 basic concepts of machine learning. The hypothesis function. All it does is it maps x's to y's, inputs to outputs. The cost function. It evaluates how well a guess is compared to the actual labeled value. And the gradient descent. This algorithm right here for linear regression, which uses calculus to zero in on the best guess. Now, last thing I want to say, and I am literally going to say this a dozen or more times this semester. Machine learning does not guess randomly. It never guesses randomly. It uses mathematics. If it guessed randomly, it would take forever to come up with the best guess. Even if we were clever and did some very, I'll just stick with clever, some very clever ways to kind of make it pseudo-random, it's still going to take forever when you get to complicated models. But because we use calculus, we are guaranteeing that it is going to reach our best guess efficiently. That's something that guessing doesn't do. Okay? Machine learning does not guess randomly, ever. If you have an algorithm that's guessing randomly, it's not machine learning. Okay? Just throw it out the window. It's not machine learning. So I hope you enjoyed this. Tomorrow we'll actually work through the actual calculus so that we can then use the formula that we come up with inside of code. We will code it into Python and run it so you can see how it works. And hopefully you'll enjoy it. I hope you enjoyed the lecture. We'll pick up tomorrow with more linear regression. Take care, everyone.